What is Linux? Unveiling the kernel. Introduction. Linux is more than just an operating system. It is the beating heart of much of the modern digital world, embedded in smartphones, powering supercomputers, and quietly running the servers that make the internet work. But when we speak of Linux, what we're often referring to is not just one system, but a family of systems sharing a core, the Linux kernel. At the center of every Linux-based system lies this crucial component, the Linux kernel. It is the interface between the system's hardware and software, managing resources and enabling users to interact with the machine in a coherent, efficient, and secure way. In this exploration, we will delve deep into the essence of Linux by unveiling its kernel, its design philosophy, internal architecture, processes, memory management, device interactions, security, and evolution. 1. The kernel defined. What is a kernel? A kernel is the core part of an operating system that manages system resources and communication between hardware and software. It has full control over everything in the system. Types of kernels. Monolithic kernel, all OS services run in kernel space. Microkernel, minimal core services, other services run in user space. Hybrid kernel, combines aspects of both. Exokernel, minimal abstraction, direct hardware access to apps. Linux uses a monolithic kernel but with modular capabilities, allowing dynamic loading/unloading of kernel modules. 2. The history of the Linux kernel. 1991, Linus Torvalds, a Finnish student, releases Linux v0.01, inspired by Minix. GPL license, Linux was released under GNU General Public License, fostering open collaboration. Community and corporations, rapid evolution thanks to contributions from individuals, academia, and corporations like IBM, Red Hat, Google, and Intel. 3. Linux kernel architecture. The architecture of the Linux kernel includes various key components. A. Process management. Handles creation, scheduling, and termination of processes. Scheduler, decides which process runs when. Preemptive multitasking, ensures fair CPU time allocation. Process states, running, ready, blocked, etc. Context switching, swapping process states efficiently. B. Memory management. Manages allocation and protection of memory. Virtual memory, each process gets isolated memory. Paging and swapping, efficient use of physical memory. Slab allocator, efficient caching mechanism. OOM killer, handles out-of-memory scenarios gracefully. C. File systems. Supports multiple file systems, extension 4, XFS, BTRFS, etc. DFS, virtual file system abstraction layer to unify file system interaction. Block devices, managed through buffer cache and I/O scheduler. D. Device drivers. Kernel modules that interact with hardware. Character devices, byte stream devices like keyboards. Block devices, storage devices. Network devices, Ethernet, Wi-Fi interfaces. E. Networking. Linux has a full TCP/IP stack. Socket layer, unified interface for network communication. NetFilteritables/NFTables, packet filtering and firewall capabilities. Routing subsystem, supports static and dynamic routing protocols. F. Interprocess communication, IPC. Mechanisms for process communication. Signals. Pipes and FIFOs. Message queues. Semaphores. Shared memory. 4. Kernel space versus user space. Kernel space runs with full system privileges, errors can crash the system. User space, isolated environment for running applications, safer. Linux maintains a clear separation to ensure system stability and security. 5. Kernel development model. Open source, maintained by thousands of developers worldwide. Versioning, follows a versioning scheme like 6.9.0. Linus Torvalds, maintains the mainline kernel tree. Release cycle, new stable release approximately every 9 to 10 weeks. 6. Kernel modules. Loadable kernel modules, LKMs. Add functionality without rebooting. Examples: device drivers, file systems, network protocols. Tools: modprobe, insmod, rmod, lsmod. 7. Boot process and the kernel. Steps from power on to login prompt. 1. BIOS/UEFI, initializes hardware. 2. Bootloader, grub/lilo loads kernel. 3. Kernel initialization, detects and initializes hardware, mounts root file system. 4. Init/systemd, initializes user space. 8. System calls and the kernel interface. System calls allow user applications to request services from the kernel. Common calls: read, write, fork, exec, wait, open. Linux provides a syscall table that maps syscall numbers to kernel functions. 9. Security and the Linux kernel. Security is deeply embedded in the kernel design. User privileges, UID/GID based permission system. Capabilities: fine-grained privilege separation. LSM, Linux security modules, SELinux, AppArmor, etc. Namespaces and groups, isolate processes and manage resources. 10. Kernel optimization and tuning. Admins and developers can tune kernel parameters. /proc and /sys, pseudo file systems for kernel runtime data. SYSCTL, adjust kernel parameters like vm.swappiness, net.ipv4.tcp _sync cookies. Real-time kernels, modified kernels for deterministic response times. 11. Kernel debugging and development tools. Tools and techniques used to interact with and debug the kernel. DMESC, view kernel messages. Probe/trace/perf, low-level tracing tools. GDB with QEMU, kernel debugging in a virtualized environment. Kernel panic analysis, stack traces, memory dumps. 12. The role of Linux in modern computing. Linux and its kernel are everywhere. Servers, dominates cloud and web server infrastructure. Desktops, Ubuntu, Fedora, Arch. Mobile, Android runs a modified Linux kernel. Embedded systems, routers, TVs, IoT devices. Supercomputers, all of the top 500 supercomputers run Linux. Containers. Technologies like Docker and Kubernetes depend on kernel features like namespaces and groups. 13. Contributions and community. Linux Foundation, coordinates efforts, supports kernel developers. Corporate contributions, Intel, Google, Red Hat, Oracle. Developer tools, Git, created by Linus, mailing lists, patch review system. 14. Challenges and future directions. Scalability. Handling systems from tiny microcontrollers to massive clusters. Real-time performance. Efforts like PreemptRT bring deterministic timing. Security hardening. Mitigating kernel exploits with tools like KASLR, eBPF sandboxing. eBPF, extended Berkeley packet filter. Enable safe, high-performance kernel instrumentation without modifying source. Rust in the kernel. Integrating memory-safe Rust code to reduce vulnerabilities. Conclusion. Unveiling the Linux kernel is akin to peering into the engine room of a vast technological vessel. It is a marvel of engineering, scalable, modular, secure, and efficient. As an open-source project, the Linux kernel exemplifies what global collaboration can achieve. From managing process lifecycles to orchestrating complex I/O operations, from maintaining robust security to enabling modern cloud-native architectures, the kernel is indispensable. Understanding the kernel isn't just academic. It's a journey that empowers developers, administrators, and curious minds alike to appreciate the backbone of digital civilization. Whether you're writing low-level drivers, securing infrastructure, or simply exploring how your computer works, the kernel is your gateway. Unveiling the Linux kernel, Part 2, Advanced Theory and Internals. 15. Kernel Design Principles. The Linux kernel is built on several foundational principles. A. Portability. Written primarily in C, with limited assembly. Easily portable across architectures, x86, ARM, PowerPC, RISC-V, SPARC, MIPS. Clean abstraction layers separate architecture-specific code from core logic. B. Modularity. Support for loadable kernel modules, LKMs. Devices and features can be compiled as modules and loaded/unloaded on demand. C. Stability versus innovation. Balances being conservative in stability-critical areas and experimental in features like eBPF, Rust integration. Maintained by a massive, well-coordinated upstream process. D. Performance and scalability. SMP, symmetric multiprocessing, support. NUMA, non-uniform memory access, optimizations. Per CPU data structures to avoid contention. 16. Advanced process scheduling. Completely fair scheduler, CFS. Default scheduler for normal processes. Implements fair queuing to ensure each task gets an equitable slice of CPU time. Uses red-black trees to efficiently select the next task. Tracks virtual runtime of each task. Real-time scheduling. SCHED_FIFO, SCHED_RR for strict priority-based scheduling. Used in time-critical applications, telecom, audio, robotics. Deadline scheduler. Added in Linux 3.14. Guarantees scheduling within a specific deadline. 17. Advanced memory management. Page tables and address translation. Multi-level page tables, improves performance and reduces memory usage. Handles translation look-aside buffer, TLB, management. Copy on write, COW. Optimizes fork by deferring physical memory duplication until needed. Transparent huge pages, THP. Reduces TLB pressure by using larger memory pages. Improves performance for memory-intensive applications. Kernel same-page merging, KSM. Deduplicates identical memory pages across virtual machines or processes. 18. Linux namespaces and control groups. Together, these form the foundation of Linux containers. Namespaces. Isolate resources between processes. PID, process IDs. Net, network interfaces, routes. MNT, mount points. UTS, hostname, domain name. IPC, interprocess communication. User/group IDs. Time settings. Control groups. Manage and limit CPU, memory, disk I/O, and network usage. Provide resource accounting, hierarchical grouping. Vital for tools like Docker, Kubernetes, LXC. 19. Virtualization and containers. The Linux kernel has native support for virtualization technologies. KVM, kernel-based virtual machine. Converts the Linux kernel into a Type 1 hypervisor. Works with QEMU for full virtualization. Containers. Rely on namespaces plus groups. Container runtimes, Docker, Containered, Podman, use kernel features like CRUD, pivot_root, secump. 20. File systems and storage stack. File system architecture. Modular, easy to add support for new file systems. Popular file systems. Extension 4, default for most distributions. XFS, high-performance journaling. BTRFS, supports snapshots, checksums, compression. F2FS, optimized for NAND flash memory. Journaling. Provides crash consistency by logging metadata changes. I/O scheduler algorithms. CFQ, deadline, NOOP, BFQ, balance throughput and latency. Chosen based on workload and storage device, e.g., SSD versus HDD. 21. Security in depth. Mandatory access control, MAC. Linux Security Modules, LSM, interface enables MAC frameworks. SE-Linux, NSA developed, strict policies. AppArmor, profile-based access control. SMAC, simplified mandatory access control kernel. Kernel address space layout randomization, KASLR. Randomizes memory layout at boot to prevent exploits. Secump, secure computing mode. Restricts system calls accessible by processes. Integrity Measurement Architecture, IMA. Ensures files and binaries haven't been tampered with. 22. eBPF, a revolutionary feature. eBPF, Extended Berkeley Packet Filter, is a kernel-safe VM for executing sandboxed programs. Monitor system performance and trace execution paths. Networking, XDP for high-speed packet processing. Security, enforce custom syscall filters, LSM hooks. Observability, real-time tracing with tools like ptrace. 23. The kernel and Rust. As of kernel 6.1+, Rust support has been merged. Provides memory safety guarantees. Used for new drivers and subsystems. Coexists with C, gradually expanding use. Diving into the shell, your command line interface. 1. The essence of the shell. The Linux shell is a user interface that allows interaction with the operating system through textual input. Unlike graphical interfaces, which rely on visual metaphors such as windows, icons, and menus, the shell emphasizes symbolic and procedural interaction, granting users granular control over their systems. It translates human intentions into precise system actions. More than an interface, the shell embodies a paradigm, the user as programmer, the system as a toolkit, and computing as composition. It's a layer of abstraction over the kernel that retains transparency, making it indispensable for tasks that require precision, automation, or introspection. 2. Historical origins and evolution. The shell's ancestry traces back to early Unix systems, particularly the Bourne shell developed in the 1970s at Bell Labs. It was designed not just to run commands interactively but to be fully programmable, functioning as a scripting language for system tasks. This dual nature, both interactive and scriptable, defines the Unix shell philosophy. Over time, different shells evolved, each building on its predecessors. Enhancements addressed usability, scripting power, extensibility, and performance. Bash became the de facto standard in GNU/Linux systems, while ZSH, KSH, and Fish introduced usability and productivity innovations. 3. The shell as an abstraction layer. Conceptually, the shell is an intermediary between user space and the kernel. It abstracts away the complexities of system calls, process creation, I/O management, and file navigation. It interprets human-readable commands and dispatches them in a form the operating system can execute. The shell doesn't manage resources directly. Instead, it orchestrates system utilities, leveraging the kernel's APIs. In this sense, it's a metaprogramming environment, a system for composing and sequencing actions rather than performing them intrinsically. 4. Interaction model. The shell operates on a read-evaluate-print loop, REPL. It waits for input, parses the input, evaluates it, typically by launching programs or invoking built-in functionalities, and then returns the output. This loop creates a dynamic feedback system, fostering a conversational computing model. Its interactivity makes it ideal for exploratory computing, while its determinism and predictability support reproducibility and automation. These dual qualities give the shell its unique position in the software stack. 5. Environment and state. The shell maintains an internal environment, a collection of named variables that represent system and session state. This environment contextualizes command execution, reflecting aspects such as user identity, working directory, system paths, language settings, and more. Unlike GUI sessions, which hide system state behind icons and forms, the shell exposes and empowers state management. Users are encouraged to reason about, modify, and extend this state, aligning the shell closely with principles of transparency and control. 6. Philosophy and design principles. The shell embodies the Unix philosophy: small tools, composability, clarity, and empowerment through simplicity. Rather than constructing monolithic applications, the shell encourages combining minimal programs to perform complex tasks. Key principles include modularity: commands do one thing well. Composability, outputs can be chained into inputs. Textual interfaces, human-readable, scriptable formats. User empowerment, no artificial limits on what the user can do. These principles make the shell both a user interface and a system design ideology. 7. Role in system operation. From system startup scripts to user logins, the shell plays a pivotal role. It's used to configure services, initialize environments, and orchestrate workflows. In servers, embedded systems, and cloud environments, shell interaction remains central even when graphical interfaces are absent. System administrators rely on the shell to diagnose problems, manipulate configuration files, and control processes. Developers use it to build, test, and deploy applications. Its universality makes it the lingua franca of system interaction. 8. Cognitive model. The shell's textual nature fosters an abstract model of computation based on pipelines, filters, and flow. It shifts the user's mindset from direct manipulation to symbolic composition. Rather than clicking a button, the user specifies a transformation, a higher-order action. This mental model is deeply aligned with programming and mathematics. It encourages logical reasoning, abstraction, and structured thinking, making the shell a tool not just of control, but of learning. 9. Ergonomics and expressiveness. Though often seen as intimidating, the shell offers profound expressiveness. A single line can embody decisions, loops, conditions, and data transformations. Unlike GUI interfaces, which can become cumbersome for repetitive tasks, the shell's symbolic input thrives on repetition, automation, and parametrization. Its learning curve is steep, but its payoff is immense. Mastery of the shell often marks the transition from novice to power user, from operator to system designer. 10. Scripting as system programming. Shell scripting transforms the shell from a command interpreter to a programming language. Scripts capture behavior, encapsulate knowledge, and automate workflows. They allow systems to be programmed rather than operated. Though simple in syntax, shell scripting is Turing-complete and structurally expressive. It integrates deeply with the system's capabilities, process control, I/O, file systems, environment, making it uniquely powerful for operating system automation. 11. Portability and universality. The shell is one of the few computing interfaces that transcends platforms. Scripts written decades ago often still function. Unlike GUI tools bound to specific systems or windowing environments, the shell's universality lies in its text-based abstraction and reliance on POSIX standards. In cloud computing, containers, embedded devices, and distributed systems, the shell remains the one consistent control surface. Its resilience and adaptability make it future-proof. 12. System introspection and reflection. The shell invites exploration. Through introspection, examining environment variables, running processes, open ports, users gain a deep understanding of system behavior. The shell acts as a microscope, offering visibility into components often obscured in higher-level interfaces. This self-reflective capability fosters literacy in computing, enabling users to diagnose, debug, and refine their systems with precision. 13. Interactivity versus automation. Shell usage spans a spectrum, on one end, real-time interaction, on the other, full automation. It can be used spontaneously to perform a task or formally to define a complete workflow. This flexibility, interactive responsiveness combined with scriptable precision, is unique. It empowers both novice users experimenting in real time and expert users defining complex orchestration pipelines. 14. Cognitive ergonomics and tool mastery. The shell rewards deep familiarity. Frequent users develop fluency, navigating directories, filtering data, and managing files with ease. Like a musical instrument, the shell becomes an extension of the mind, translating intention into action almost reflexively. Over time, this mastery fosters efficiency and insight, a distinctive form of literacy grounded in the logic of computation and system structure. 15. Security implications and responsibility. Power comes with responsibility. The shell's access to system internals makes it a double-edged sword. capable of configuring, optimizing, or devastating a system. Misused commands, unchecked scripts, or environment mismanagement can have catastrophic effects. Thus, security-conscious shell usage is crucial. This includes understanding permissions, validating inputs, managing credentials, and auditing scripts. The shell is as much a security boundary as it is a tool. 16. Evolution and future trends. While GUI environments have dominated consumer computing, the shell has never faded. In fact, it's resurgent in modern infrastructure. DevOps, cloud-native systems, containers, edge computing, all rely on shell-centric paradigms. The rise of automation, infrastructure as code, and minimalist computing has revived appreciation for the shell's composability and expressiveness. Even modern user-centric shells aim to blend tradition with usability, offering syntax highlighting, auto-suggestions, and contextual help. 17. Comparative interfaces. Compared to GUI and touch interfaces, the shell is unique in being declarative and symbolic. It emphasizes what to do over how to do it. Rather than manipulating representations, users manipulate abstractions. Its verbosity may seem like a disadvantage, but it enables clarity, auditability, and documentation. Where GUIs may obscure state, the shell reveals it, often in terms that can be versioned, shared, and reused. 18. Learning path and pedagogy. Learning the shell is a rite of passage. It begins with memorizing basic structures and grows into an intuitive understanding of how systems behave. Over time, users develop a mental model of the file system, processes, and execution flow. Pedagogically, the shell offers immediate feedback, encouraging experimentation. Unlike compiled languages, where the feedback loop is long, shell commands respond instantly, a key factor in their pedagogical power. 19. Philosophical underpinnings. At a deeper level, the shell represents a philosophy of computing where the user is in command, not constrained by the interface. It favors clarity over concealment, composition over encapsulation, and adaptability over rigidity. The shell enshrines the idea that the computer is a tool, not a black box. It cultivates agency, responsibility, and understanding, values as relevant today as they were in the early days of Unix. 20. Conclusion: the shell is an interface to power. The Linux shell remains one of the most powerful user interfaces in computing history. It offers a transparent, scriptable, and extensible way to interact with the system, one rooted in logic, clarity, and control. To use the shell is to engage directly with the soul of the system. It is where abstractions meet action, where users become creators, and where computing becomes a craft. Its longevity and relevance are a testament not just to its design, but to the enduring human desire for clarity, expression, and mastery. File system hierarchy: navigating the Linux landscape. Introduction. The Linux file system is not merely a way to store data, it is a meticulously organized hierarchy that reflects the structure and philosophy of the Unix operating system. Unlike file systems designed with graphical interfaces in mind, Linux's structure prioritizes clarity, modularity, and systemic accessibility. The File System Hierarchy Standard, FHS, maintained by the Linux Foundation, formalizes this organization and ensures consistency across distributions. Understanding the file system is foundational to mastering Linux. It defines where programs reside, where configurations live, where logs accumulate, and where temporary or user data is stored. As we explore its design, significance, and purpose, we uncover the logic that underpins every Linux-based system. 1. The philosophy of the file system. Linux follows the Unix philosophy: everything is a file. This conceptual model blurs the distinction between system components. Hardware devices, processes, configuration, and even the kernel interface are exposed as files in the hierarchy. This design choice provides uniformity, a consistent interface to interact with system resources. Modularity, components can be replaced or modified without altering the entire system. Transparency, users can introspect, trace, and manipulate system behavior through the file system. The Linux file system is more than a directory tree, It is a map of the operating system's architecture. 2. Root and the tree structure. At the top of the hierarchy is the root directory, symbolized by a // symbol. This is not to be confused with the root user. The root directory is the entry point to the entire system. All files, devices, and mounts descend from this point. The hierarchy resembles an inverted tree, with / at the base and subdirectories branching outward. This structure avoids the drive letter model used by Windows, C, D, etc., and presents a single, unified namespace. 3. The primary directories and their purpose. /root. The top-level directory. Every single file and directory is contained under it. The system boots from this directory. /bin, essential user binaries. Contains essential command line binaries required for system repair, booting, and single user mode. Commands like ls, cp, mv, bash, cat, and echo reside here. Available even when only the root partition is mounted. /spin, system binaries. Contains binaries for system administration, used by root or during system initialization. Includes fsck, mount, shutdown, and iptables. /etc, configuration files. The nerve center for system and application configuration files. Each subdirectory and file configures specific services, e.g., /etc /ssh /etc /stab /etc /password. Does not contain executables or binaries. /dev, device files. Hosts special device files that represent physical and virtual devices. Includes files like /dev /sda, hard drives, /dev/null, /dev/random, /dev/tty. Managed dynamically by UDEV. /proc, process information. A virtual file system exposing information about running processes and the kernel. Files like /proc/pinfo, /proc/meminfo, and /proc/pid/ reflect real-time data. Crucial for introspection and debugging. /sys, system information. Another virtual file system, offering information and interfaces to kernel subsystems and devices. Replaces some /proc roles in newer kernels. /lib and /lib64, essential shared libraries. Contains shared libraries needed by binaries in /bin and /spin. Analogous to DLL files in Windows. /lib64 is used for 64-bit systems and multi-architecture support. /usr, user system resources. A massive subtree that holds read-only user applications and libraries. Structured like the root. /usr/bin, user programs. /usr/spin, admin binaries. /usr/lib, shared libraries. /usr/share, architecture-independent data. Historically mounted separately, it's the most populated directory. /var, variable data files. Stores data that changes frequently. Logs, /var/log. Mail spools, /var/mail. Caches, lock files, PID files. Ensures system writes do not occur in read-only /usr. /tmp, temporary files. Temporary storage used by applications. Files are typically deleted on reboot or after a defined period. Access permissions can vary, but it's globally writable, 1777 sticky bit. /home, user directories. Each user has a personal directory. /home/Alice, /home/Bob. Stores user-specific configuration, downloads, documents. Important for system backup and migration. /root, root user's home directory. Distinct from /, it is the home directory for the superuser, root. Isolated from /home for security and access control. /boot, bootloader files. Contains the Linux kernel, initial RAM disk image, initd, and bootloader, e.g., grub. Configs. Must reside on the root partition or a dedicated partition. Essential for startup, corrupting it can render the system unbootable. /opt, optional / third-party software. Used for add-on packages and commercial software. Applications installed here don't follow the strict FHS layout. Common in enterprise systems for software like Oracle, MATLAB, etc. /media, removable media mount points. Temporary mount points for USB drives, CDs, SD cards, etc. Automatically populated by desktop environments. /MNT, mount point for manual mounting. Traditionally used by system admins for temporary mount points. Unlike /media, it's not managed automatically. /run, runtime data. Stores volatile, runtime-specific information, e.g., service PID files, sockets. Replaces older uses of /var/run. 4. Logical segregation and partitioning. The structure also enables logical partitioning. Directories can be mounted on separate disks or file systems. /home on a different partition for user data protection. /var isolated to prevent log files from filling up /boot on its own for systems with complex boot configurations. This design enhances security, performance, and manageability. 5. Symbolic and hard links. The hierarchy is often supplemented by symbolic links that alias directories or files to other locations, e.g. /lib/usr/lib, /bin/usr/bin. This simplifies access and enhances compatibility while retaining structure. 6. Virtual file systems and pseudo-files. Directories like /proc and /sys contain virtual files, which do not exist on disk but are dynamically generated by the kernel. They allow programs to read system state or interface with kernel modules using the same file I/O functions used on regular files. 7. Security and permissions. Every file and directory is governed by permissions: read, write, execute, and ownership, user and group. The hierarchy is a key mechanism for access control. System binaries are typically owned by root. User files reside in /home and are owned by respective users. Directories like /etc., /boot, /spin are critical and tightly restricted. Security policies like SE-Linux or AppArmor extend this model with mandatory access control, MAC. 8. File naming and case sensitivity. Linux is case-sensitive. README, and README are different. Special characters are allowed but discouraged. Files with leading are hidden, e.g., .bashrc. These conventions, combined with the hierarchy, reinforce a structured and predictable environment. 9. Role and package management. Package managers like apt, dnf, pacman install files into the FHS structure. Binaries to /usr/bin. Libraries to /usr/lib. Configs to /etc. Docs to /usr/share/doc. This predictability supports automation, reproducibility, and system integrity. 10. Mounting and file system types. The Linux hierarchy supports mounting other file systems. Local disks, extension 4, XFS. Network file systems, NFS, CIFS. Pseudo file systems, procs, SYSFS. Each mounted system integrates seamlessly into the tree, no separate letters or paths. 11. Hierarchy in minimal and embedded systems. In embedded Linux systems, the hierarchy is often trimmed. Minimal /bin, /lib, /etc. No /usr, /home, or /var. All-in-one file system, initramps or squashs. This modularity allows Linux to scale from tiny IoT devices to massive supercomputers. Permissions demystified, controlling access and security in Linux. Introduction. In the Linux operating system, permissions serve as the foundation of security, access control, and system integrity. Linux, like its Unix predecessor, is inherently a multi-user system. Its architecture is designed to enable multiple users to coexist securely, preventing unauthorized access and ensuring privacy and data protection. Permissions in Linux dictate who can read, write, or execute files and directories. While seemingly simple on the surface, Linux permissions are a deep and nuanced system of access management encompassing traditional Unix permissions, extended ACLs, access control lists, file attributes, and security modules like SELinux or AppArmor. This document explores the Linux permission model from the ground up, aiming to demystify its structure, application, and role in maintaining a secure computing environment. 1. The basics of Linux permissions. Every file and directory in Linux has an associated set of permissions defining three operations. Read, R, permission to view the contents of a file or list a directory. Write, W, permission to modify a file or the contents of a directory. Execute, X, permission to run a file as a program or script, for directories, the ability to traverse into it. These permissions apply to three categories of users. Owner, U, the user who owns the file. Group, G, a group assigned to the file. Others, O, all other users. The permissions are typically represented as a string of 10 characters, such as RWXRXR. The first character denotes the file type, for file, D for directory, L for link. The next 9 characters are grouped into triplets, RWX, owner, RX, group, and R, others. 2. Ownership model. Each file or directory has a user owner, typically the creator. A group owner, usually the primary group of the user at creation. Ownership can be modified using chown, changes owner and group. CHGRP, changes group ownership. This model enables fine-grained access control while maintaining simplicity. 3. Understanding file and directory permissions. File permissions. Read, R, allows viewing contents, cat, less. Write, W, allows editing the file. Execute, X, allows running the file as a program or script. Directory permissions. Read, R, lists contents with ls. Write, W, allows creating, deleting, or renaming files within the directory. Execute, X, allows entering the directory, CD, and accessing metadata of files. Note, write permission on a directory without execute is ineffective, you can't access its files. 4. Changing permissions, chmod. The chmod command alters permissions. There are 2 modes. Symbolic mode. Chmod u plus x file. Chmod gw file. Chmod o equals our file. Operators. Plus adds a permission. Removes a permission. Equals sets permission explicitly. Numeric, octal, mode. Permissions are encoded using octal notation. Symbol binary octal. R104. W0102. X0011. Thus, RWX equals 7. RW equals 6. R equals 4. 3 digits represent user, group, and others. Chmod 755 script.sh hashtag RWXRXRX. Chmod 644 file.txt hashtag RWRR. 5. Special permission bits. Linux supports 3 special permission bits. Setuid, S on user bit. When set on an executable file, the program runs with owner privileges, not the users. Useful for system binaries like /usr/bin/password. Chmod u plus s file. Permission string, RWSRXRX. Setjid, S on group bit. On a file, executes with the group owner's privileges. On a directory, new files inherit the directory's group. Chmod g plus sdir. Directory string, DRWXRSRX. Sticky bit, T on others bit. When set on a directory, commonly /tmp, only the file owner can delete or rename their files. Enhances security in shared directories. Chmod plus T/shared. Directory string, DRWXRWXRWT. 6. File attributes, chatter. Beyond basic permissions, Linux has file attributes providing advanced controls. Using chatter and lsatter. Immutable. File cannot be changed or deleted. Append only. File can only be added to. Extents format, used by extension for. Example. Chatter plus IMportant.txt. These attributes are stored at the file system level and respected by the kernel. 7. Extended ACLs, access control lists. Traditional permissions are limited. ACLs allow more granular control over individual users and groups. Key tools. getFacle, view ACLs. setFacle, modify ACLs. Usage example. setFacle mu Alice, our file.txt hashtag grant read access to Alice. setFacle mg devs, rw file.txt hashtag grant rw access to group devs. ACLs provide flexibility but increase complexity and management overhead. 8. umask, default permission mask. The umask determines default permissions when files or directories are created. Common default umask, 0022. File creation default, 666. Directory default, 777. Final permissions equals default umask. Example. 666,022 equals 644 new files, RWRR. 777,022 equals 755 new DIRs. RWXRXRX. Use umask to set appropriate security defaults for user environments. 9. Root and superuser privileges. The root user is exempt from most permission constraints. This power is essential for system administration but dangerous if misused. To limit damage, users can use sudo for privilege escalation. Avoid logging in directly as root. Audit root actions carefully. Access to sudo is governed by /etc/sudoers. 10. SELinux and AppArmor. Linux distributions support Mac, mandatory access control, via security frameworks. SELinux, Security Enhanced Linux. Developed by NSA. Uses contexts and policies to define access beyond traditional permissions. Enforces rules even on root. Example context. User_u object_r httpd_sys_content_t s0. AppArmor. Simpler alternative. Uses profile-based control of applications. Easier to configure but less granular than SELinux. These systems protect against privilege escalation, misconfigurations, and zero-day exploits. 11. Real-world scenarios. Web server files. Files owned by www.data. Permissions, 644 for files, 755 for directories. Avoid 777, which poses serious security risks. Shared directories. Use group ownership and setgid. Control access with ACLs. Public writable directories. Use sticky bit to protect users' files. 12. Common security pitfalls. Loose permissions, 777, open files to abuse. Incorrect setgid usage can lead to privilege escalation. Misconfigured ACLs can allow unintended access. Disabling SELinux without reason weakens system security. Administrators must audit permissions regularly and avoid blanket permission changes. 13. Auditing and monitoring. Monitoring file access helps detect breaches. Use audit for real-time monitoring. Use find to locate world writable files. Find /type fperm-0002. Use LSL, getFacle, and SATA for inspection. Periodic audits are essential for hardened systems. 14. Permissions in networked environments. In NFS, Samba, or cloud storage. Permissions may reflect the client-side system. User IDs, UIDs, must be synchronized across hosts. Masking, mapping, or ACL translation can occur. Consistency is key to maintaining security in distributed setups. 15. Permissions in containers and virtual machines. Containers share the host kernel but isolate file access via namespaces. Capabilities. AppArmor/SE Linux profiles. Mounting files into containers requires explicit permission mappings. In VMs, Linux permissions are respected natively by the guest OS. Mastering permissions is mastering control. Permissions are the backbone of Linux system security. They enforce the boundaries between users, define the capabilities of processes, and safeguard the integrity of the system. While the syntax and commands may appear arcane, the logic behind permissions is elegant and rooted in decades of robust design. Understanding Linux permissions is not just about file access. It's about governing authority, ensuring safety, and enabling collaboration in a shared computing environment. Whether managing a personal server or architecting an enterprise system, mastery over permissions empowers you to wield the full potential of Linux securely and responsibly. Package management in Linux, installing and updating software. Introduction. At the heart of every Linux distribution lies a critical subsystem known as package management. It is responsible for installing, updating, configuring, and removing software. Unlike Windows or Mac OS, where users frequently download standalone installers or rely on centralized app stores, Linux software is distributed through packages, managed by powerful tools and repositories. Package management is a defining feature of Linux. It provides systematic control over software and their dependencies, facilitates automation, ensures security through digital signatures, and enables large-scale system administration through scripting and orchestration. This document presents an exhaustive theoretical exploration of Linux package management, focusing on package formats, management tools, dependency resolution, software repositories, and best practices across various distributions. 1. What is a package? A package in Linux is a structured archive that contains the software application or component, metadata, version, dependencies, description, configuration scripts, pre-install, post-install, removal hooks, file manifest, which files are placed where. Packages are typically formatted for a specific distribution. .deb, Debian and derivatives, e.g., Ubuntu. .rpm, Red Hat-based systems, e.g., Fedora, CentOS, RHEL. Other formats, .tar.zst, Arch Linux, Snap, Flatpak, AppImage. Packages are essential for version control, software validation, and automated management. 2. Roles of a package manager. A package manager is a tool or suite that installs packages and their dependencies, updates software consistently across the system, removes packages cleanly, resolves complex dependency graphs, interfaces with software repositories, verifies software integrity via cryptographic signatures, maintains package databases. Different distributions ship different managers. Distribution package format tools. Debian/Ubuntu.deb dpkg, apt, aptitude. Red Hat/Fedora.rpm rpm, DNF, yum. Arch Linux source/binary pacman. Gentoo source-based portage, emerge. Alpine Linux.apk apk tools. 3. Software repositories. A repository, repo, is a centralized storage location for packages. Types. Official repositories, maintained by distribution developers. Community repositories, managed by community contributors, e.g., Arch User Repository. Third-party repositories, provided by vendors or projects, e.g., Docker, Google Chrome. Local repositories, internal mirrors for offline or secure environments. Repositories are configured via configuration files. Debian-based/etc/app/sources.list. Red Hat-based/etc/yum.repos.d/star.repo. Repositories provide indexes for fast search and updates, GPG keys for package signing, architectural support, x86_64, ARM, etc. Staging, stable, testing, unstable, for software lifecycle management. 4. Dependency resolution. A critical function of a package manager is dependency resolution. Most software depends on libraries and other tools. Challenges. Dependency hell, conflicts between versions or circular dependencies. Orphan dependencies, installed but unused packages. Version pinning, maintaining compatibility without upgrades. Conflicting packages, two packages install overlapping files. Modern package managers use dependency graphs, version constraints, and metadata to resolve these issues automatically. Some systems, e.g., Gentoo, use flags or build time options, adding further complexity and flexibility. 5. Installing software. Debian-based systems, APT. APT, Advanced Package Tool, works on .deb packages. apt-update, refreshes package indexes. apt-install package, installs a package and dependencies. apt-remove package, removes package, config files may remain. apt-purge package, removes package and configuration files. APT supports pinning versions, simulating installations, dry runs, and cache management. Red Hat-based systems, DNF. DNF, Dandified Yum, is the successor of Yum. DNF install package. DNF remove package. DNF check update. DNF history, view transaction logs. DNF clean all, clear metadata. Arch Linux, Pacman. Pacman handles both binary and source-based packages. Pacman S package, install. Pacman R package, remove. Pacman SCI, sync package database. Pacman SU, full system upgrade. Pacman uses PKGBUILD scripts to define package builds and supports AUR, Arch User Repository, for community-driven software. 6. Updating software. Updating packages ensures that the system has security patches, bug fixes, performance improvements, feature enhancements, methods, rolling release, continuous updates, Arch, Gentoo. Point release, periodic stable releases, Debian, Ubuntu LTS. Hybrid, Fedora combines rolling development and point release for stability. Commands. apt-upgrade, Debian. DNF upgrade, Fedora. Pacman SU, Arch. Updating can involve kernel upgrades, configuration file merging, service restarts, database migrations. Package managers track version history and may provide rollback mechanisms, e.g., DNF history undo. 7. Removing and cleaning packages. Software removal is vital for freeing disk space, reducing attack surface, preventing version conflicts. Commands. apt-remove package. apt-auto-remove, clean up unused dependencies. DNF remove package. Pacman RNS package. Cleanup actions may involve removing orphaned libraries, clearing package caches, /var/cache/apps/archives, /var/cache/pacman/package. Purging configuration files. Package managers avoid deleting shared libraries if they're required by other software. 8. Configuration management. During installation, configuration files are deployed, usually to /etc. Package managers mark conf files as user modifiable. Provide options to keep or replace configs on update. May use .pocnew or .dpkgdist suffixes for safe merges. Tools like etkeeper, diff, or manual inspection help maintain configurations across updates. 9. Package verification and integrity. To ensure software authenticity, Linux package managers use GPG signing. Check SHA-256/MD5 checksums. Validate package metadata. Each repository is associated with trusted keys. If a package is modified or unsigned, the manager will issue warnings or halt the installation. Commands: apt-key, GPG, DNF repo query verify, RPMK. Security best practices include regularly refreshing keys, auditing sources, verifying downloaded packages before manual installation. 10. Meta packages and virtual packages. Meta packages contain no data but depend on a group of other packages, useful for installing environments, Ubuntu Desktop, KDE Plasma. Ensuring consistency, Build Essential. Virtual packages allow generic dependency resolution. Example: apt install mail transport agent might install postfix, exim, or nullmailer. 11. Alternative packaging systems. Traditional package managers are evolving with containerized or sandboxed alternatives. Snap, Canonical. Self-contained packages. Automatic updates. Isolation through confinement. Common in Ubuntu systems. Flatpak. Cross-distribution packages. Sandboxed applications. User-specific and system-wide installation. AppImage. Portable applications. No installation required. Executable with Chmod plus X. These systems prioritize ease of use, distribution independence, and sandboxing, but often sacrifice disk efficiency and integration with native system management. 12. Source-based and custom package systems. Gentoo, Portage. Source-based distribution. Uses a build scripts. Highly customizable via use flags. Offers performance and minimalism. Linux from scratch. Manual source compilation. No package manager unless added. Educational approach to system building. Custom systems require compilation infrastructure. Dependency tracking, manually or via tools. Configuration management. 13. Automation and scripting. Administrators use package managers and scripts for provisioning new machines, CI/CD pipelines, cloud deployment, backup and rollback. Tools like Ansible, Puppet, Chef integrate with package managers. Shell scripts, apt install Y, DNF update Y, automate manual tasks. 14. Offline and air-gapped systems. For secure environments, packages can be downloaded, apt download, yumdownloader, pacman SW. Stored in local repositories. Verified with detached GPG signatures. Tools like apt caching or repo sync aid in repository mirroring and offline updates. 15. Challenges and best practices. Common pitfalls. Mixing repositories from different distributions. Installing .deb or .rpm manually without resolving dependencies. Using outdated keys or expired repositories. Ignoring broken dependencies or update failures. Best practices. Stick to official and trusted repositories. Perform regular full updates. Use package pinning carefully. Test upgrades and staging before production. Clean up unused packages periodically. Conclusion. Package management is a cornerstone of Linux systems. It abstracts the complexity of software distribution into a manageable, reliable, and secure process. From dependency resolution to sandboxing, package managers empower users to control their software environment with precision and efficiency. Mastering package management is essential for anyone working with Linux, whether as a casual user, system administrator, or developer. It is not just about installing software, it's about embracing the modular, open, and secure philosophy that defines Linux itself. Introduction. Linux, at its core, is a command-line-oriented operating system, offering users the ability to interact directly with the system using commands. The command line interface, CLI, is not just a relic of the past, it is a powerful tool embraced by system administrators, developers, and power users for its speed, flexibility, and control. Understanding essential Linux commands is the foundation for mastering system administration, shell scripting, server management, and even basic tasks. This guide delves deeply into the theoretical understanding of essential Linux commands, explaining their structure, usage contexts, variations, and importance in day-to-day Linux operations. 1. Structure of a Linux command. Every Linux command typically follows a general structure. Command, options, arguments. Command, the executable or built-in shell instruction. Options, flags that modify the behavior of the command, e.g., help. Arguments. Targets or inputs the command acts upon, e.g., files, directories, users. Example. lsl/home/user. ls is the command. L is an option, long listing format. /home/user is the argument, target directory. 2. File and directory management. ls, list directory contents. Displays files and directories. lsl, detailed list view with permissions. lsa, includes hidden files. lslh, human readable sizes. cd, change directory. Moves between directories. cd/etc, moves to /etc. cd, moves up one level. cd, goes to the home directory. pwd, print working directory. Shows the current directory path. mkdir, make directories. Creates one or more directories. mkdir new_folder. mkdir p parent/child, creates parent and child directories recursively. rmdir, remove empty directories. Deletes empty directories. Use rmr to remove non-empty directories. rm, remove files or directories. Deletes files or directories. rmfile.txt, removes a file. rmrdir, recursively removes a directory. rmf, force deletion, suppress warnings. cp, copy files or directories. Duplicates files or directories. cpsource.txt destination txt. cprsrc/dest/, recursive copy. mv, move or rename. Moves or renames files and directories. mv old name new name, renames. mvfile.txt temp, moves to another location. 3. File viewing and text processing. Cat, concatenate and view. Displays file contents. catfile.txt. Less/more, paginated viewing. Scroll through file content. Less logfile.log. Use /search_term within less. Head/tail, view start or end. Head n10 file.txt, first 10 lines. Tail f logfile.log, real-time log viewing. grep, search within text. Finds text patterns using regular expressions. grep error logfile.log. grep by warning, case insensitive. cut/awk/sed, text manipulation. cut d:/f1/etc/password, extract fields. awk, print $1, print first word. sed s/old/new/g, replace text. 4. File permissions and ownership. chmod, change permissions. Sets file permissions. chmod 755 script.sh, rwxrxrx. chmod plus x file, adds executable bit. chown, change ownership. Changes user and group ownership. chown user group file. chgrp, change group. Changes group ownership. chgrp developers project. umask, default permissions. Controls default permission mask for new files. 5. System information and monitoring. uname, system info. uname a, all system details. df, disk usage. dfh, human readable disk space usage. do, disk usage of files/folders. do/sh folder/, summary of folder size. top/top, process monitoring. top, live view of processes. Top, enhanced version with UI. PS, process snapshot. PSAUX, full list of running processes. Free, memory usage. Free M, memory in megabytes. Uptime, system load. Shows how long the system has been running. 6. Package management, varies by distribution. Debian/Ubuntu, apt. Apt update, update package list. Apt upgrade, upgrade installed packages. Apt install name, install package. Red Hat/Fedora, DNF/Yum. DNF install package. Yum update. Arch Linux, Pacman. Pacman SU, update system. 7. User and group management. Huami, current user. Shows the logged in username. ID, user and group IDs. Displays user UID, GID, and groups. Add user/user add, create users. Add user new user. User add M user. Password, change password. Password, change current password. Password user, change another user's password, admin only. Group add, create groups. Group add devs. User mod, modify users. Usermod AG sudo user, add user to group. 8. Networking commands. IP/ifconfig, network info. IP address show, IP addresses. Ifconfig, older tool. Ping, test connectivity. Ping google.com, send ICMP packets. Netstat/SS, network connections. SS-Toln, list listening ports. curl/get, fetch content. curl http://example.com. get https://example.com/file.zip. SCP, secure copy. SCP file user at host/path, remote copy over SSH. 9. Disk and file system commands. Mount/amount, manage mount points. Mount/dev/sdb1/mnt. Amount/mnt. LSBLK, block devices. Shows disk and partition structure. Fdisk/parted, partitioning. Fdisk/dev/sda, edit partition table. MKFS, create file system. mkfs.ext4/dev/sdb1, format with extension 4. 10. Archive and compression commands. tar, archiving. tar cvfarchive.tar file/. tar xvfarchive.tar, extract. gzip/gunzip. compress/decompress.gz files. Zip/unzip. Zip format support. xz/bzip2. Other compression formats. 11. Search and find utilities. Find, locate files by criteria. Find/name star.conf, find.conf files. Find. Type fsize +1g, files larger than 1 GB. Locate, fast file search. Locate file name. Uses an indexed database, run updated to update. 12. Job and process management. And, background tasks. Command and, run in background. Jobs, view background jobs. FG/BG, foreground/background control. FG%1, resume job in foreground. BG%1, resume in background. Kill, terminate process. Kill PID, send signal. Kill -9 PID. Force termination. 13. Shell environment and customization. Echo, print to terminal. Echo $HOME, prints value of home. Export, set environment variable. Export path equals $PATH/new/path. .bashrc.profile, .bash_profile. Startup files for environment configuration. Alias, shortcut commands. Alias LL equals LSL. 14. Permission and security utilities. Sudo, execute as superuser. Sudo apt update. Su, switch user. Su username. Chmod, chown, umask. Already covered in permissions. 15. Shell scripting fundamentals. Though not commands themselves, understanding control structures helps with automation. If, for, while, case. $, command, or backticks command for command substitution. Exit, return, trap for flow control. Shell scripts extend the power of basic commands through logic and structure. Mastering essential Linux commands equips users with the ability to navigate, control, and manage Linux systems effectively. Each command, though simple in syntax, carries powerful implications when used correctly and creatively. With consistent practice, these commands form the toolkit for success in the Linux ecosystem, whether for personal use, professional system administration, or development. From manipulating files to managing networks, Linux commands form the foundation of all higher-level operations and scripting. Understanding their theory not only aids in usage but also empowers users to write robust automation, troubleshoot systems, and understand the inner workings of one of the most powerful operating systems in the world. Introduction. Mastering Linux is a journey, not a destination. While you may now have a solid foundation in essential commands, file systems, permissions, package management, and shell navigation, the Linux ecosystem is vast and constantly evolving. Continuous learning is essential for becoming a proficient user, system administrator, or developer. This guide provides a comprehensive theoretical overview of the best avenues and structured resources to deepen your Linux knowledge over time. 1. The philosophy of lifelong Linux learning. Linux is built on principles of openness, collaboration, and modularity. As such, the knowledge base is not centralized but distributed across communities, documentation, source code, and experiential learning. Understanding how to effectively access and engage with these learning mechanisms is crucial. Curiosity-driven learning leads to organic growth. Community engagement fuels problem-solving and innovation. Hands-on experimentation reinforces theoretical understanding. 2. The importance of documentation. Linux systems are incredibly well documented. Learning how to interpret and utilize official documentation is a vital skill. Man pages, manual pages. The man command provides the most direct form of documentation available on nearly every Linux system. Man ls explains usage, options, and flags for the ls command. Sections are categorized: 1 equals user commands, 5 equals file formats, etc. Info pages. An alternative to man pages, offering more detailed navigable text. Info corutals provides extensive help on core commands. C/usr/share/doc. On many distributions, package-specific documentation is stored here in plaintext or HTML. Online documentation. Most distributions maintain extensive, searchable web-based manuals. ArchWiki, highly regarded, even by non-Arch users. Debian and Ubuntu docs, structured for user-friendliness. Red Hat documentation. Enterprise-grade, detailed technical material. 3. Books and written guides. Introductory. The Linux Command Line by William Schatz, a beginner-friendly yet comprehensive guide. Linux Pocket Guide by Daniel Barrett, concise command references. Intermediate. How Linux Works by Brian Ward, explains what happens beneath the surface. Unix and Linux System Administration Handbook by Evie Namath et al., widely used in universities and workplaces. Advanced. Linux Kernel Development by Robert Love, a primer for kernel enthusiasts. The Art of Unix Programming by Eric S. Raymond, philosophical and architectural insights. 4. Online courses and MOOC platforms. Online courses provide structured learning paths, often including labs and assignments. edX and Coursera offer university-backed programs in Linux and system administration. Linux Foundation courses like Introduction to Linux on edX are free with optional certification. Udemy and Pluralsight. Commercial platforms with instructor-led video tutorials. Topics range from Linux basics to DevOps and advanced Bash scripting. See YouTube. Free channels like DistroTube, Learn Linux TV, and the Linux Experiment offer tutorials, reviews, and demonstrations. 5. Forums, Q&A, and community portals. Participating in forums not only helps solve problems but also deepens understanding. A. Stack Exchange, Ask Ubuntu, Unix and Linux. Community-reviewed answers and reputational feedback systems. B. Reddit communities. /r/Linux, /r/Linux for noobs, /r/Linux admin cater to users of all levels. See linuxquestions.org. One of the oldest and most comprehensive Linux forums. D. Distro-specific forums. Arch, Fedora, Debian, Ubuntu all maintain active community support forums. 6. Mailing lists and IRC/chatrooms. Many open-source projects and distributions use mailing lists for coordination and support. Use Gmain, Mail Archive, or official distro list archives. IRC, e.g., #Ubuntu, #ArchLinux on LiberaChat. Or Matrix/Discord communities for live chat and collaboration. 7. GitHub, GitLab, and source-based learning. A. Reading source code. Explore source repositories of open-source projects to see how tools are implemented. Commands like cd, ls, cp are all part of packages like kruttles or util Linux. Explore code on GitHub/GitLab, study pull requests, issues, and commit history. B. Contributing. Start with simple documentation fixes or translation contributions. Graduate to debugging and feature implementation. Learn about project workflows, version control, and community etiquette. 8. Labs, practice, and simulation environments. A. Try HackMe and Over the Wire. Practice Linux security and command line challenges in gamified environments. B. Linux from Scratch, LFS. A project and book that teaches you to build your own Linux system from source. C. Practice Labs. Websites like Katacoda and Play with Docker provide in-browser terminals for real-world simulations. D. Virtual machines. Tools like VirtualBox, VMware, and QEMU allow you to experiment with different Linux distributions safely. 9. Certifications and structured programs. For those seeking professional recognition or structured pathways. A. Linux Foundation certifications. LFCS, Certified System Administrator. LFCE, Certified Engineer. B. CompTIA Linux Plus. Widely recognized for entry-level IT professionals. C. Red Hat Certified System Administrator, RHCSA. Industry standard for enterprise environments. D. LPI certifications. Vendor-neutral certifications by the Linux Professional Institute. Each certification provides a structured curriculum that guides learners through progressive stages of competency. 10. Building real-world projects. Learning theory is vital, but projects bring everything together. Possible project ideas include creating shell scripts, automate backups, monitoring, or reporting. Setting up servers, web server, Apache/Jinx, mail server, file server. Home lab infrastructure. Install and manage Docker, KVM, Ansible, Kubernetes. Linux as a daily driver, customize your environment, manage .files, tweak the window manager. Real-world application reinforces theoretical concepts through problem-solving, error tracing, and iterative refinement. 11. Staying updated. Linux is constantly evolving. It's crucial to stay updated to remain competent. A. RSS feeds and news sites. LWN.net, Linux Weekly News. Phoronix, Hardware/Linux Performance. OMG. Ubuntu. Desktop news and tutorials. B. Blogs. Follow developers, distribution maintainers, and kernel contributors. C. Git watchlists. Subscribe to notifications for updates in kernel, systemd, kruttles, etc. 12. Specialization paths. As you progress, consider focusing on a specialization that aligns with your goals. System administration, security and hardening, DevOps and CI/CD, embedded Linux, kernel development, cloud native/Linux and cloud, Kubernetes, Docker. Each specialization has its own stack of tools, communities, and learning resources. Tailor your exploration accordingly. 13. Open source culture and ethics. Being part of the Linux ecosystem means embracing its culture of collaboration, transparency, and contribution. Respect licenses, GPL, MIT, BSD, etc. Attribute work appropriately. Engage with humility and openness to learn. Encourage newcomers and pay it forward. Understanding the ethical and cultural foundation of Linux will enhance not just your technical skills but also your professional reputation and contribution potential. 14. Organizing your learning. Use tools like note-taking apps, Obsidian, Joplin, command cheat sheets, mind maps for topics and dependencies, task managers, Trello, Notion, to track goals. Being methodical accelerates comprehension and retention. Linux mastery is a layered and evolving endeavor. There's no single path, just a rich terrain of opportunities. By combining core documentation, structured learning, community participation, practical application, and self-directed curiosity, you can grow from a novice to an expert at your own pace. The ultimate goal is not merely to learn commands but to understand the Linux philosophy, internalize system behavior, and contribute to its vibrant ecosystem. Each terminal session is a step forward in your journey, and with the right resources and mindset, there's no limit to what you can achieve.